Welcome to Maths with EJD. In this video, I'll be talking about the conjugate gradient method being another uh, example under the gradient-based methods for numerical optimization. Gradient-based methods. So far we've seen gradient descent. That was the first one, gradient descent. You've seen Newton's method, which improves on gradient descent by involving the second derivatives called the Hessian matrix, the Hessian of the original matrix, right? So we have the first and second derivatives. The first derivatives are the gradients, and we have the second derivatives, which gives us the matrix called Hessian. And then now we are going to consider the conjugate gradient method. Conjugate gradient method. Okay. So like I said, so far we have seen we have seen gradient descent, we've seen Newton's method. Now we're going for conjugate gradient method. So conjugate gradient method. Okay. Now let's see what that is actually about. First of all, the conjugate gradient method. So going forward, I'll just call it CGM. CGM is an iterative algorithm. It's an iterative algorithm for solving systems of linear equations of the form AX equals B, where A is a symmetric, really important point to note. A is a symmetric positive definite, positive definite um matrix. A is a symmetric positive definite matrix. My very first playlist on this channel is on matrices. So I have up almost 20 videos, if not more than 20, on matrices, and I defined all these terms like symmetricity, positive definiteness, and the rest of them. So if you want to check that up in case you don't know what this mean already. So where A is a symmetric positive definite matrix, then X is the vector of unknowns, the vector of unknowns which you are looking for, vector of unknowns, and B is the known vector. That's the right hand side. B is the known vector. Okay. Now, um, CGM is particularly useful. It is particularly useful for large sparse systems, large sparse systems where direct methods, where direct methods like Gaussian elimination. In the series on numerical analysis, I've actually dealt with both direct and iterative methods for solving systems of linear equations. Okay, where direct methods like Gaussian elimination would be computationally expensive, Okay, so let's look at some steps of the conjugate gradient method. So the first step is initialization. Okay. So here, first of all, you choose an initial guess. Choose an initial guess, X naught, and it's often the zero vector. That's 0, 0 or 0, 0, 0, depending on the dimension of the matrix. Often, what was I writing there? Often, right? The zero vector, often the zero vector. Okay. Then next, we compute the initial residual. Compute the initial residual, which is R naught, which is equal to B minus AX naught. Okay, that's the initial residual. Of course, that's like the difference between the known part and the other side, right? So then we set the initial search direction, which is P naught, and that is equal to the initial residual also. P naught is equal to R naught. Important. Then that's just for step one, talking about initialization. So we can go for step two. I guess I'll use this lighter green. So the second point would be the iterative process. Iterative process. So in this situation, is this a very good color choice? Okay, let me just go. Iterative process. I think it's always good to have something brighter. I mean, just switch over, sort of. So two is the iterative process. Iterative process. Let me make it cuter. This okay. Iterative process. So which say for each iteration, K compute. So we have a lot of things to compute. It can be quite tasking. So compute the step size, compute step size alpha K. And how do you do that? It is such that alpha K is equal to RK transpose RK. So the initial search direction that we have from the beginning, RK transpose RK, and then we have PK transpose APK, like that. So we have that one. Then the next thing we do is after computing the step size alpha K, we update the solution estimate, the solution estimate. And the way to do that is to say xk plus 1 is equal to xk plus alpha k pk. And then we have rk plus 1, which is equal to rk minus alpha k apk. This is quite a lot, I think. Then the next, we update the direction vector. Update the direction vector. So to update the direction vector, that's beta k equals rk plus 1 transpose rk plus 1. So whenever we have this transposition and all that, it is some kind of normalization. So then we have rk transpose rk. Okay. So again, we also have pk plus 1 equals rk plus 1 plus beta k pk, like that. So we have all of that. So uh, uh that's step two. Then we can, for step three, we can then have this. We have three where we repeat. So repeat the solution, repeat until the solution converges. Repeat until the solution converges. And what would that mean? That is when the absolute value of Rk is sufficiently small, is sufficiently small. So that's like the stopping criteria in this case. Okay. The stopping criteria is that the absolute value of Rk is sufficiently small. Mind you, this is Pk plus 1 equals Rk plus 1 plus beta k Pk. Okay, so we have all of these things for the conjugate gradient method. Of course, these things don't stick really until we have examples. So let's talk about that. We have an example now. Let's consider a simple system, a simple system of linear equations, of linear equations. That is, you have say what should I call this? Let me say this is 4a plus b equals 1. Should I say a and b since we are going to have a and b here? So let me say something like 4p plus q equals 1. Then p plus 3q equals 2. Yeah, I think this works. Again, we have p and r already. This is quite a challenge. Okay, let me see what else I can say. Of course, I could just go straight and have the matrix, right? Let me say 4w plus z. Okay, this works. 4w plus z equals 1. And then w plus 3z equals 2. So that's the system we have. So if you have this system, right, of course, in matrix form, this is simply a equals um a equals 4, 1, 1, 3 easily. And then our x would just be w and z, right? And then our b would be 1, 2. So because we're talking about ax equals b, that's what that looks like. So with that in place now, we can start solving. Let's start with the first one, initialization. Initialization. Okay. So the first thing is start. Start with an initial guess. Initial guess. X naught equals 0, 0. Okay. Then once we've done that, we compute the residual. Compute the residual. So that means that R naught is equal to B minus AX naught. And that is B. We know B to be 1, 2 minus A. A is, what's that A? A is 4113. 4113. And X naught would be 0, 0. Of course, obviously, we see this is 0 automatically. So we see that R naught is just the known vector b. Okay, so here R naught is just equal to b. So R naught is 1, 2, easy. So then the next thing we do is the first iteration. So going for the first iteration, that's like step 2. We have first iteration. So for the first iteration, we compute, first of all, compute alpha naught. So to compute alpha naught, we have alpha naught equals R naught transpose R naught all over P naught transpose A P naught, P naught transpose A P naught. And that is equal to, what is R itself? Now R is 1, 2, right? So that is 1, 2, 1, 2, like this, all over P naught. Do we know P naught yet? Yeah, of course we know that P naught would also be R naught, right? I think that is how that is supposed to be. So we have P naught. Interestingly, this we know that from one step, the initial P naught is R naught. Basically, that's what I just want to confirm. So we know that P naught P naught is equal to R naught, which is 1, 2 again. Okay. So we have that. So P naught is 1, 2. Then we have A, which is A is 4113. A is 4113 into P naught, which is 1, 2 in this situation. So we can dissolve all that. So A naught, I mean alpha naught, is actually, so for the top we have 1, 2 against 1, 2. Okay, 1, 2, 1, 2. So we have 1, 2, 1, 2 up there. 1, 2, 1, 2 all over. Then when we come down, we have 1, 2 first. And then here, since we have two rows of this, we have 1, 2, 1, 2. And then we have 4, 1, 1, 3 over that. All right. So that we alpha naught is equal to, for the top now, we have 1 squared plus 2 squared. Then down here, we have 1, 2 into 1 times 4. So basically, we have 1 into 4 plus 2 into 1. Just trying to make that clear. And we have 1 multiplied by 1 plus 2 multiplied by 3. So that means we have 1 times 4, 4. I mean, 2 times 1 times 4, 2 times 1. Then 1 times 1 plus 2 times 3. So alpha naught is equal to 1 plus 4 up there divided by still 1, 2 here into 4 plus 2, 6. Then 1 plus 5 is also 6, I think. So it's 6 apiece. I guess that's the idea. Yeah. 1 times 1, 1. 2 times 3, 6. So that's 7, right? That should be 7. That should be 7. Hope that's correct. 6, 7. So 1 times 4, 4. 2 times 1, 2. 4 plus 2, 6. Then 1 times 1, 1. 2 times 3, 6. Plus 1, 7. Yeah, that's what we have. So we have alpha naught now is equal to 1 plus 4. The 1 plus 4 up there is 5 all over, that's 5 all over 6, 7. Then 1, 2 like this. So that alpha naught is equal to 5 all over 6 times 1, 6, 7 times 2, 14. Okay, 7 times 2 is 14. So that we now have alpha naught to be 5 over 20. Interestingly, that is 6 times 1 is 6, right? 7 times 2 is 14. I believe that's correct. That is 1 over 4. That's 1 over 4, or if you like, 0.25. Okay, that looks like the way to go. So that is alpha naught. So with alpha naught in place now, the next thing we want to do, once we compute alpha naught from all the steps, right? Okay, so yeah, we compute alpha naught this way, which we have done, and then we can do the updates. X1 will be X naught plus alpha naught P naught. Then R1 will be R naught minus alpha naught AP naught. Okay, let's go for that also. I guess I want to switch over, right? Say this is now, um, so since we have got alpha naught, then we have X1. What is that thing even called? So I can name it appropriately. Yeah. What is that? I think it's updating. We're updating, right? So update the solution estimate. Okay. So now we have the solution estimate. Solution estimates. It's not what we are doing now. So we have X1 equals X naught plus alpha naught P naught. And we have all of these things in place. So X1 is X naught, of course, is 0 vector 0, 0. Okay, plus alpha naught, that's what we just got, which is 0.25, or if you like, 1 over 4 into P naught. P naught is at 1 over 2, 1, 2 rather. P naught is 1, 2. We have 1, 2. So I think at this point, okay, let me see if I can preserve the fractions. So this is 0, 0 plus 1 over 4, then 1 over 2. I think that makes sense. So that x1 now is equal to 1 over 4, 1 over 2, like that. So that is our x1. Then the other thing is the r1, okay? So we can have r1 now. Let's say r1 is r naught minus alpha naught a p naught, okay? So r1 is equal to r naught is the same thing as p naught, which is still 1, 2, right? R naught is p naught. That is still 1, 2. Okay, so this is 1, 2. Alpha naught is just what we it was what we just got now, which is 1 over 4. So we have 1 over 4 into A. A again is 4, 1, 1, 3, 4, 1, 1, 3 into P naught, which is 1, 2. So R1 is equal to 1, 2, then minus 1 over 4, okay, into, so you have 1, 2, 1, 2, then you have 4, 1, 1, 3, okay. That's taking care of this now. So R1 is equal to 1, 2 minus 1 over 4 into 4 plus 1. I mean, 4 times 1 is 4 plus 2, that's 6. 1 times 1 is 1, 2 times 3, 6. So this is 7, okay? The 7, so that we have R1 to be equal to 1 over 2, 1, 2 minus 6, 6 over 4, 7 over 4, okay? So we have R1 now to be, let's quickly do this. 1 minus 6 over 4. I think it's easier since we know that 1 is 4 over 4. So 4 over 4 minus 6 over 4. That's minus 2 over 4, which is minus 1 over 2. Then R1, the second, is um that's 8 over 4. 2 is 8 over 4 minus 7 over 4. That will be 1 over 4. Okay, so that is R1 taken care of easily. So with that done, so we can go for beta knots. Okay. It's quite a task. So what's that now? Yeah, so we've got that. So we update the direction vectors, right, with these two expressions. So update the direction vectors. Okay. So switch gears and we update direction vectors. This is just the first iteration. So update direction vectors. Okay, so to update direction vectors, we have two expressions. The beta naught is equal to R1 transpose R1 all over R naught transpose R naught, I believe. Yeah, to update direction vectors. So yeah, so beta naught is R1 transpose R1. I mean yeah, R1 transpose R1, then R naught transpose R naught. Then we have P K plus 1 to be R1 plus beta naught P naught. Okay, we come to that later. So of course, the first thing we want to do here is this R1 transpose R1. So what is R1? Okay, we have R1. The transpose of R1 will just be minus 1 over 2, 1 over 1 over 4 into minus 1 over 2, 1 over 4 this side, divided by R naught. I think R naught is the 1, 2. If I still remember very well, R naught is 1, 2. R naught and P naught is the same. To be very sure, R naught is 1, 2, yes. So we have 1, 2, 1, 2, like this. So that beta naught now is equal to, so for the top, we have minus 1 over 2, 1 over 4, then minus 1 over 2, 1 over 4. Okay, at the top, then all over same. Now we have 1 over 2, 1 over 2, like this. So that's like beta naught is equal to, at the top, we have 1 over 4 plus 1 over 16. I think that's correct. Then down here, we have 1 plus 4. That's 1 squared plus 2 squared. Okay, so beta naught is equal to, so LCM of 4 and 16 is 16. So 4 and 16 is 4. 16 here is 1. So all over 5 Okay, 4 plus 1, 1 plus 4 is 5. So beta naught is equal to 5 over 16 divided by 5 over 1. So that beta naught is equal to 5 over 16 times 1 over 5. This cancels out. So the beta naught in this case is equal to 1 over 16. So this is beta naught right here. Of course, other important things we have got before. This is R1. We got also X1. Okay. We got, yeah, okay, I think I circled this as required. So this is 1 over 16 here for beta naught. Now, um, with this in place, we go for still talking about the direction, right? So we go for say this now, P1. P1 is R1 plus beta naught P naught. Okay. So P1 is equal to R1 again. R1, we just got minus half 1 over 4, right? So P1, that's minus half 1 over 4 plus beta naught, which is 1 over 16 into P naught. P naught again is 1, 2, I think. Yeah. P naught is 1, 2. Yep. P naught is R naught for sure. So that's 1, 2. So we have P1 to be minus 1 over 2, 1 over 4, plus 1 over 16, then 1 over 8, if you like. So then we can do the smart thing. We just add these two together, right? So this you have minus 1, so minus 1 over 2 is like minus 8 over 16 plus 1 over 16. Just match the 16s together. So this is like minus 7 over 16 for the first one. And for the second one, this is like 1 over 4 is like 8 over 1 over 4 is like 2 over 8. Okay, 2 over 8 plus 1 over 8. So that is 3 over 8. Okay, to match the status, 3 over 8, like that. And this goes. So now that you have updated all this, then we can now go for the second iteration. Don't forget the first iteration is already done to be x1. So, x1 is just x naught plus alpha naught p naught. That's x1. So so we can then go for the second iteration. So since we have all this in place now, so we can have the second iteration. Let me go this way. So that should be like step 3, right? Each step is pretty long. First iteration. So 3 now is second iteration. 3, we have the second iteration. So what I'm just going to do here is I'll just get the x2 and then I'll go to the Python code. So again, so we got x1 before. X1 is x naught plus alpha naught p naught. So it means x2 will be x1 plus alpha 1 p1. x2, x2. So second iteration, we have x2 is equal to um interestingly, I have to check again. X2. Okay, let me see that again. X2 is is x1 plus alpha 1. So it's x alpha p, right? X plus alpha p. Okay. So x2 is x1 plus alpha 1 p1 basically. So that means x2 is equal to x1. What is this x1 now? X1 is 1 over 4, 1 over 2. X1 is 1 over 4, 1 over 2 plus alpha 1. Do we have alpha 1 yet? I think so. If you don't have alpha 1, then that's some trouble, right? Okay, we can get alpha 1. Oh, yeah. Do I want to go through this? Okay, we can get alpha 1. I think I can still take the pain. Alpha 1 is R naught, R naught transpose. So R naught, P naught, A P naught. Okay. So we need alpha 1, right? So alpha 1 is um alpha 1 will be R1 transpose R1 all over P1 transpose A P1 K into P1 itself. So I think, okay, we already have P1 to be minus 7 over 16, minus 7 over 16, then 3 over 8, 3 over 8. Okay, so we have to sort this part out now. So this is actually alpha 1, is alpha 1. So this is alpha 1. So let's sort out alpha 1. I thought I could just get over that easily, but let's go. I've signed up for this. R1, right? R1 is, where's R1? Do we have R1? If we don't have it, okay, yeah, R1 is minus of 1 over 4. Okay. All right. So R1 is minus half 1 over 4. That is R1. Okay. Then P1. I think we also have P1 just now. Minus 7 over 16, 3 over 8. Okay. So this will be minus half 1 over 4. Then P1 is minus 7 over 16, 3 over 8. Minus 7 over 16, 3 over 8 into A now. We have A is 4113. That's the A we started is 4113. Then P1. So P1 is minus 7 over 16, 3 over 8, like this. So that alpha 1 is okay, I think we already know. Anytime we have that, it's just minus half squared plus 1 over 4 squared. So I don't waste time with that. And then we come to this other side. Of course, this one we have to leave it to minus 7 over 16, 3 over 8. And then the next one, the next one is okay. So this is minus 7 over 16, 3 over 8. Then we have 4, 1. Then minus 7 over 16, 3 over 8. And we have 1, 3. Okay. I want to, okay, yeah, this works. So that alpha 1 is now this is 1 over 4 plus 1 over 16 at the top. Then down here we have minus 7 over 16, 3 over 8 into so for this now we have minus 7 over 4. So that's minus 7 over 4 plus 3 over 8. Then down we have minus 7 over 16 plus minus 7 over 16 plus 9 over 8. So alpha 1 is up here we have 16. That's 4 plus 1 up there. Then down here we have minus 7 over 16, 3 over 8 into, so let's tidy this up now. 7 over 4 is like minus 14 over 8. So that's minus 14 plus 3. That's minus 11 over 8 up there. Then down here we have minus 7 over 16 plus 18 over 16. So 18 minus 7. 18 minus 7 is 11, I believe, all over 16, right? Yeah, 18 over 16. Okay, so alpha 1 again is 5 over 16 at the top, all over. So again, we have this. So I mean, this is easy peasy. So we have minus 7 over 16 multiplied by, okay, we can say minus 7 over 16. Okay, let me just do my normal thing for easy understanding. Minus 11 over 8, then 11 over 16. And we have minus 7 over 16, then 3 over 8. Maybe not as easy because of the big numbers. So alpha 1 is 5 over 16 at the top. And down here we have 77 over 8 times 8 is 64. 64 times 2 is 128. So we have 77 all over 128 plus 33 all over 128. Okay. Yeah, 8 times 8 is 64 times 2. Okay. So alpha 1 is 5 over 16 divided by 33, 77 plus 33, that's 10, 110. That's 110 all over 128. So alpha 1 is simply 5 over 16 times 128 all over 110. So we can tidy that up. We have 16 times 4 is 64 time. So 16 here is 1. Uh yeah, so that's 8 times, right? 8. So this is 8. 8 times 6 is 48. Then 8 times 1. Yeah, that works. Then we have 5 here is 1. And 5 here is 5 and 11 is 2. Uh then 5 in 5 and 11 is 2. Okay, 5 in 100 is 25. 5 and 10 is 2. That's like 27, right? No, that can be 27. Mm, 5 goes in 100 20 times. So that's 22. Yeah, that's 22. So finally, we have 4. Alpha 1 is 4 over 11 in short. Alpha 1 is 4 over 11. That's a lot. If I knew it was going to be this, I'll just go straight to the Python code. But now I'm down. I've put myself here, so it's okay. So we have x2 finally. So x2 now. So we go back to x2. So x2 is equal to, we'll start again. X2 is 1 over 4, 1 over 2. So that's 1 over 4, 1 over 2. Then the other side is alpha. So this alpha 1, which you have got, minus 7 over 16, 3 over 8. Okay. So plus 4 over 11, minus 7 over 16, and 3 over 8. Okay. Believe that's what it should be. Yeah, I think that works. Okay, so let's tidy things up here now. So x2 is equal to 1 over 4, 1 over 2 plus, so if you put that inside, so 4 goes in 16 4 times, so we have minus 7 all over 11 times 4, that's 44. I think that works. Yeah, 4 in 16, that's 4. So 4 times 11 is 44. So yeah, then down here we have 4 in 8, 2. So that's 3 over 22. 3 over 22, I believe. Is that correct? I think so. Yep. 4 over 11 times 3 over 8. So 4 here is 1, 4 here is 2. So that's 3 over 22, correct. 3 over 22. Yeah, thankfully, I can just get x2 and just go to Python. So 1 over 4 plus 1 over 4 minus 7 over 44. So 1 over 4 is like 11 over 44 minus 7 over 44. Okay, so this is like 4 over 44, which is 1 over 11. 4 over 44, yeah, is 1 over 11. So this is 1 over 11. Then when we come here, this is like 11 over 22, right? 11 over 22, that's 1 over 2. So 11 plus 3 is 14. So we have 14 over 22. 14 over 22 is 7 over 11. Okay, so that goes. So if I go to get these ones in fraction, this approximately 1 over 11. 1 over 11. Okay, let me quickly get that. I could as well just do everything since I've brought myself this far. So, okay, calculator. Okay, 1 over 11. 1 divided by 11 is 0.0909. Okay, then 7 over 11 will just be 7 times this, right? 7 over 11 is 0.6364. Okay, that's the second iteration, right? So with the second iteration now, we yeah, so we have that result. So that takes us, we can now go to the Python code and see what we have there. So this is the Python code. Okay, I already have the answer run, so let me clear this out and try to explain afresh. Okay, yeah, look at this. So we define the conjugate gradient method with all the necessary, there's a lot to define, so you can just study it. You see it on Facebook for sure, but you won't be able to get it on YouTube. But if you follow me on Facebook, you can copy this code out and run it on your own and try to tweak all these things. So just try to study because this is getting long already. But this is where the matrix is defined 4113. The right hand side is 1, 2, and all the other process is defined right there. So if you run it now, you see that it tallies with what I've just got. So it's more like, I started with W something, I think WX or something like that. So we have after two iterations, we have zero. Interestingly, this actually converges after two iterations where we get 0.09 because I think we expected to take the absolute value of R1 or so. I think that's what we're supposed to do to know that it has converged. I think there's a condition for that stated. Yeah, RK. Okay, RK. So now the result is exactly what I got by hand already. So that means you can see that the conjugate gradients converges very fast. So this is the second iteration, right? So let's see. Oh, so it means I'm going to need R2. Do I have time to compute R2? That's going to be a whole lot. Let me see what it takes to do R2 if I can cope with that. If not, I'll just leave it at the level of Python code. So where is R1 itself? Where is R1? Okay, this is how we got R1. Okay. Mm, I, I think we can easy I think it's easy to pull this off, right? So this is R1. So to get R2 now. So because once we get solution estimate, we have estimated the first part now. So to get R1 is to get R2, that'll be R1 minus alpha 1 AP1. Okay. R2 is R alpha AP. R minus alpha AP. Okay. R minus alpha AP. So, I mean, I think I just want to take the pain to check for converge. So we have seen it converges in two iterations. So I just want to establish that. So to check for convergence, we need R. So that means R2 is equal to R1 minus alpha 1 AP1. If that is correct. Do we already have P1? If you don't already have that, then I'll just shut it down already. Okay, we have P1. Nice. That's looking good. So R1 is R no R2 is R1 minus alpha 1 AP1. So AP1. So we have R1. R1 is minus half 1 over 4. Okay. R1 is minus half 1 over 4. Okay, so R1 is minus half 1 over 4. Is that what I just saw? Is there minus? This is a lot. R1, where's R1 again? R1 is minus half. Okay, minus 1 over 4. Great. Then we need alpha, alpha 1, which I think we have found just now. So yes, alpha 1 caused a lot of uh trouble, but it's okay. 4 by 11. Then we have 4113 for that. Then P1, I hope if we have to compute anything fresh, I'm not doing it again. But I think we have P1, right? So P1 is minus 7 over 16, 3 over 8. Okay, nice. Minus 7 over 16, 3 over 8. Minus 7 over 16, 3 over 8. Can I confirm that A is still 4113? I think we just used it somewhere. A is 4113. Correct. Yeah. Okay, so we can easily calculate R2 then. Okay, can do R2. So R2 is equal to minus 1 over 2, 1 over 4, minus 4 over 11 into, so can I be smart here? I think I can be. Minus 7 over 16, 4, 1. Okay, then 3, minus 4 over 16, 4, 1. Then, oh no, it doesn't work this way. sorry, minus 7 over 16, 3 over 8. And we have 4, 1. Yeah, better. Then minus 7 over 16, 3 over 8. Okay. Then this is 1, 3. Okay. So that R2 is equal to, so I just want to be sure about the convergence, minus 1 over 2, 1 over 4, minus 4 over 11 into, so for this now, can we be smarter? This is minus, okay, 4 in 16, right? That's 4. So that's minus 7 over 4 plus 3 over 8. I think we did something close to this, not quite long. Then here we have minus 7 over 16 plus 9 over 8 also. So that R2 is minus 1 over 2, 1 over 4 plus 4, 11, 4 over 11, rather, 4 over 11 into, again, this is minus 14 plus minus 14 over 8. That's minus 11 over 8, right? Yeah, that's minus 14 over 8 plus 3. That's minus 11 over 8. Then here we have 11 over 16, right? Yeah, that's 11 over 16. Should that be what it is? So this is minus 7 over 16 plus 18 over 16, right? That's 11 over 16. So it means R2 is simply going to be minus 1 over 2, 1 over 4 plus, okay, so 11 cancels out automatically. Then we have minus half here, okay? And then this is, yeah, that's minus half there. Then down here, 11 cancels out, so this is 1 over 4 again. This is serious. Are we back here? So R2 is equal to, so we have minus half, then 1 over 4 plus 1 over 4. So that means we have R2 to be, this is minus 1, minus half is minus 1, and here is 1 over 2. So to check for convergence, we have to evaluate R2, absolute value of R2. So that's the absolute value of minus 1, 1 over 2. What that simply means is that we have absolute value of R2. What is our absolute value of R2 again? That's like I think that should be for a matrix. What is the absolute value of a matrix? That's like the determinant or something. I'm not sure. I think that should be like square root of minus 1 squared plus. No, I'm not sure. I'm not sure. Let me not be too. I think that is what it should be actually, but I'm not very sure. Mm, I think it should be that normalization thing. Yeah, but let's leave it there. But this is what R2 is. Okay, yeah, I think it's fine. Python has confirmed to us. So, um, let's say, as usual, what teachers do, we can just verify, right? Verify, verify convergence condition with this. Okay. Okay, so it looks like I have one or two practice questions. This has been a very lengthy process. Let me see if I can drop one or two questions. Okay, let me just drop this only one. Um, practice question. Practice question. Okay. Um, implement the conjugate conjugate gradient method. Conjugate gradient method for a system with A equals 3226. You see, symmetricity is important. That's why you always see this 3226 kind of thing, like 4113 the other time, and then you have B to be, and also positive definite. B is 2 minus 8. So just try this out. Do it manually, then use Python to complete it. So let me see your comments. Let me see your solution as comments, either on YouTube or Facebook. But of course, you can only get the code on Facebook. You can just follow me on Facebook and copy out the code and implement, try it, just tweak it to take care of this particular matrix and let me know what your result is like. Of course, comment, let me know how helpful this video is for you. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then afterwards, let's talk about, I mean, you know, subscribe if you have not subscribed already. If you have subscribed, thank you so much. If you have not subscribed, please go ahead and subscribe. Hit the notification bell so you can always get alerted each time a new video is released. You definitely don't want to miss other things that are coming. After this, I'm done with the gradient based methods. Maybe there are more, but these are the three I'll be taking. I've taken the gradient descent, I've taken Newton's method, and now conjugate gradient method. So from after now, I'll be going for the Nelda-Mead method, which is one of the derivative-free methods. And there'll be genetic algorithm as simulated annealing or something like that. Yeah, I think so. So you don't want to miss any of this. So come along, subscribe, and hit the notification bell. Also, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.